Okay, good morning, everyone. Before I get started today, I want to confirm one more time if you're all hearing me clearly. Is
Yes,
everyone
sir.
hearing me?
Yes, sir.
Okay, thank you so much. Thank you for confirming that. Of course, today we're having our lecture on Zoom, uh, because of what I told everyone in class last week. So, we started this material on on Monday, and of course, we're going to use this material all the way. All what we're going to be doing this week. This material actually cover that, and I also want to use this opportunity to announce to everyone that I've already published recordings. Okay, I've published my recordings, and of course, you know. Not all of that are ready, but the outstanding one will be uh published in due course. Okay, so as a recap to what we did on Monday, okay, when we're talking about sample geometry and random sampling, of course, we actually believe that in multivariate statistics, we actually seen we view the data set, as where we view every observation as a vector, okay, as a vector in p-dimensional space. Of course, the way we collect our data, we have uh, observations, where they actually collected over so many variables. And of course, we, we want to be able to uh, explain, how sampling actually behave in a high dimensional space. Of course, before now, in the theory of statistics that you've learned before, we are able to, understand the fact that uh, you know, because of the way we collect our data, we take a sample uh, randomly from a target population, and because of that, the basic statistic is a function of random variable, and because of that, we're going to say sample statistic is a random variable, mean differs from sample to sample. We expect our variance to also differ from sample to sample. We expect whatever sample statistic that we actually obtain from sample to actually differ from sample to sample. So because of the fact that we're taking random sample. Now we actually explaining the behavior in a high dimensional data where we got more than one variable. We want to be able to see the behavior of sampling, of random sampling, and not only that, we actually want to have we want to read mini to geometric interpretation. So I'm actually going to say in summary, okay, since we have our data set, to be in form of a cloud, okay, a form of a cloud. So we may be interested in the center of a cloud. We may be interested in the shape of a car of the cloud. We may be interested in the orientation. We may be interested in whatever characteristics of interest. So I'm actually going to say in general, uh, in multivariate statistics, the random sampling will transform, deterministic geometric objects. When I say deterministic geometric object, I'm talking about centers. When I say centers, I'm talking about the mean. Okay. Then we want to talk about projections, distances, into random quantity. Okay, so also distribution govern inference, estimation, accuracy, and stability. Okay, so away from that, I think I've been able to walk you through some basic statistic. Okay, this is a sample mean, the center of the cloud that I talk about. This is the sample covariance. Okay, if I actually want to understand the shape, okay, the spread, okay, then I need a sample covariance. If I want to understand relationship among variables, in such a way that a particular variable will not dominate, okay, then I'm going to talk about correlation matrix. So I think I've walked you through this the other time. All of these have geometric interpretations. Okay, so I'm quickly going to move right now to where we stop, and we're going to continue from that. I've walked you through all this on Monday. Oh, give me 1 second. Okay, so I think we stop here, and I want us to start from here, because let me tell you this. What I want to explain to you now, it has a very serious implication, okay, in statistical techniques that we all know about. I'm actually going to talk about, let me discuss this. And I'm going to tell you the connection between this and, a technique in statistics that is very, very common. Before moving forward, can somebody confirm again if you are still hearing me clearly? Is everyone still hearing me?
Yeah. Yes,
Okay,
sir.
thank you so much. I'll thank you for confirming that. Now, one of the most important statistic or measure, one of the most important measure is we want to understand the center of mass. We want to know the center of a cloud, okay? Because data point, observations in either dimension and space actually seen as a cloud. So, because of the variation, we actually want to know the center. Okay, that's why we normally want to find the mean. And don't forget, we got a lot of variables. So if I'm talking about a particular variable now, let's say this guy here actually represent the mean of a particular variable that I'm calling Kate variable. Okay, of course, I walk it through on Wednesday. Okay, I walk it through on Wednesday. That if I want to look at it geometrically, I'm actually going to say, getting the sample mean, yeah, actually occur as a result of projecting observation onto the vector of ones. When I project my observation onto the vector of ones, I'm actually going to have my sample mean. Okay, that is a geometric implication of projecting a vector. Okay, I'm going to say that again. Okay, projecting observation. Okay, the YK now represent observation of a particular variable. I may be talking about height. I may be talking about weight. I may be talking about any other variable. Okay, so projecting the observation now onto a vector of ones. Okay, you say one subscript n. You know what that means? The one subscript n means the number of one that we're gonna have. It depends on the number of observation. I'm going to say that again. If I actually have 10 observation, I'm actually going to have 10 ones. That is exactly what I mean by n. Okay, the n is a number of observation. You get what I mean? So this is the vector I'm actually talking about. Okay, so as a result of that, we're gonna get the sample mean for that particular variable. Okay, but you know what? after getting the sample mean, okay, because in statistical analysis, the moment if the mean is involved, okay, the variance will be involved because when you figure out an average, when you know the center of a cloud, you want to be able to understand how the data spread out. Okay, you want to figure out the deviation of the respective observation from the mean. Okay, now because of that, you're actually going to center, which we call deviation vector. Now, in the actual sense, when I'm talking about deviation vector, what I'm going to do is I'm actually going to be subtracting my mean from the original observation within the variable. Okay, now doing this statistically is actually to measure a distance. You want to measure the distance between the respective observation from the center. Okay, and that's what we call deviation uh, vector. But you know what? The deviation vector that we have, okay, we can also have a way to decompose that. Okay, how do we decompose that? Okay, and I need you to pay attention now because the decomposition of the deviation vector is very, very crucial, okay, in statistical inference. I'm going to say that again. The decomposition, okay, that involve deviation vector, very crucial in statistical framework in general. Now, you already know what deviation mean, right? Now, when I have a deviation vector, okay, the deviation vector is going to give me an opportunity, okay, if I want to talk about this guy now, okay, in terms of all of that. Of course, I'm actually going to have this mathematically. Okay. Now, when you take a look at what I have now, so this is more or less like I'm decomposing a particular a variable into into the mean and the deviation from the mean. Okay. I'm decomposing that. Okay, into the mean and the deviation from the mean. Now, let me tell you this. The consequences of this, of the decomposition, okay, and validates, okay, analysis of variance. I'm going to say that again. Okay, the successful decomposition, of YK that I just talked about into the mean and deviation from the mean, actually validate analysis of variance. Most of you've heard about what we call ANOVA. Okay, you know, ANOVA is actually the partitioning of the total sources of variation into various components. Okay, so when you have a total variation around the response variable, ANOVA will enable us to split that or decompose that into what I call explained variation and unexplained variation. And this is a justification of that part. Okay, this is an observation now that we actually split it into explained variation, okay, and unexplained variation. There's something I want you to see. Do you know that the deviation that we talk about here, okay, is actually the random parts of an ANOVA technique? Because the random part of ANOVA module actually represents unexplained variation. Okay? Okay, so the ANOVA module actually consists of explained and unexplained variation, and of course, the decomposition that takes place here actually validates that approach. We don't just do what we do, we got reason why we do what we do. Okay, now I'm actually moving. Okay, so this is just to showcase, this image talking about you having I-dimensional, okay? And of course, I remember the other time I walk you through how to get the mean, for each uh, variable, assuming equal weights, okay? So I think I explained that the other time. Now, coming to this example now, if I have a 2 by 4, okay, maybe if my data frame is looking like this, where I'm actually having two observations with four variables. Okay, when you take a look at this guy now, do you know we can figure out the rank of this? This is rectangular. Okay, the same way we can figure out the rank of the square matrix, we can also figure out the rank of these that are matrix. So if you take a look at what I have, let's take a look at how many independent rows do we have. So this guy is not connected with this guy. So which is actually going to give us, the rows is going to be 2. Okay, don't forget, the rank is going to be the minimum. Okay, the minimum of N and P, right? So right now, okay, here we got 2 for this one, okay, that are linearly independent because there's no way I can figure out any of the row from the other one. Now, if I now want to look at it from the column wise, let's take a look at it from column one. If you take a look at this from column, okay, you're actually going to see for all the columns here, they don't relate. So we have four independent columns. So this is going to be 4, right? What is the minimum here? The minimum is 2. So we're saying the rank of this matrix is actually 2. So if I don't want to get the rank from here, I can also obtain the correlation. Okay, I can figure out the rank from the correlation because you know why? You may be wondering that, oh, this is rectangular. This may be kind of confusing. Okay, so you can decide to get a correlation. When you get a correlation matrix, it's going to be square matrix. Now you can now see that. Okay, now take a look at this. Now let's see. We have to prove that the rank of this correlation matrix is also 2. Because this correlation matrix is coming from this data set. It's coming from this data matrix. Okay, so let's take a look at it. Let's start from the column. Okay, now we want to see if they are independent or not. Oh my God. When you take a look at this guy and this guy, they look the same. Okay, they entirely look the same. So the column 1 and column 3, okay, they depends. That is me. So if they depends, I'm also going to take a look at another one. Okay, so that is the first one. So this guy equal to that. So if this guy or if this column actually equal to this column, okay, now let's see any other one, whether there's a relationship. Take a look at column 1 and column 4. Okay, I want us to take a look at this. When I multiply this column by -1, okay, multiply all of this by -1, that will give us this. Okay, I wanted to confirm that. That's true. If I multiply this by -1, because -1 times -1, that's going to be 1. Okay, -1 times that, that's going to be that. So, which means we got, so this and this are, they are linearly dependent. So, and don't forget the other time that I said, this also equal to this one. So, from what I'm seeing now, we're actually going to take all of these as 1. All of this, 1, 2, 3, is going to be 1. We're going to take that as 1. And this is going to be the second one. Okay. Now, because of that, I'm actually going to say the rank here is 2. If you also look at it from the row perspective, it's still going to be the same. So we only have 2 independent rows and 2 independent columns here. So what I just showcase right now is just to show how you can figure out the rank of a square. matrix. Okay, I think we discussed that before. I'm just trying to remind you. Okay, so in case in the course of this lecture, if there's anyone who actually want to ask question, I want it to be interactive as ever. So you have the right to challenge me. You ask question, and I'm actually going to explain. Before moving forward, um, is there any question? Before moving forward, is there any question? If you understand what I've explained so far, I need you to say yes or you comment yes. Do you understand that?
Yes, sir.
Okay, thank you so much. Let me also read the chat. I'm reading my chat right now. Okay, I'm seeing a lot of yes. But you know what? In case you do not understand, please let me know. Now, I want to go into we're talking about deviation vector, but you know what? We also want to figure, we also want to have, can we have a way to to generate basic, statistical measure that makes sense from deviation vectors? And the answer is yes. From deviation vectors, we can actually figure out the variances. We can also figure out the covariance. And how are we going to do it? I need you to pay attention. Geometrically, okay, geometrically, okay, if you take a look at this, we actually call that the square length of the deviation vector. Of course, you know what deviation vector mean. It's actually the difference between the observation and the mean. Okay. Now, uh, in a matrix form, this is what I mean. Okay. In a matrix form, you're actually going to see that I'm talking about the two vectors here. They represent the same deviation vector for a particular variable, except that we transpose one, we use it to multiply the other one. But do you know, if I want to show results in a scalar form, there is the expression in scalar form is this guy. Hmm. This is looking like a sum of square. Okay, this is what we call sum of square deviation from the mean in statistics. So what are we talking about now? So it means, geometrically, what we call the square length of deviation vectors is actually the same as the sum of square deviation from the mean. That is one of the geometric interpretation that we're talking about. Now, if I have this as a sum of square deviation from the mean, okay, if you take a look at what I have here, of course, we make use of this in analysis of variance. Okay, we make use of this a lot. If you want to talk about the sum of square or treatment or whatever. Okay, so if I now if I now divide this by a sample size, then that is actually going to give us variance. Okay. And of course, in statistics, we normally want to talk about variance. Okay. But do you know I can also obtain the covariance, from the combination of two different vectors? Okay. Now, if I want to get the covariance now, because without covariance, there's no way we're actually going to get to correlation. Of course, you know what covariance does. Now, right now, if you take a look at what I have now, so if I have two different vector, I have a deviation vector K, I have another deviation vector I. Can you see that? So I'm having two different deviation vector now because I'm considering two variables. One represent one variable, the other one represent the other variable. It's like you're computing the deviation from the deviation vector from a different variable. Okay. And you know what? This is in scalar form. This is what we have in scalar form, which we call in statistics, we call that sum of cross products. Sum of cross products. But you know what? If we divide this by n, we divide by the n, we're actually going to have covariance. Okay? We're actually going to have covariance. I just wanted to see that. Okay, now the next I want to talk about another important measure that we can figure out geometrically that also have statistical implication is what we call the correlation. Do you know the angle? Because in geometry, we normally want to talk about angles between vectors. I'm going to say that again. You have two vectors, okay? Of course, they actually going to have a angle between them in dimensional space. Okay, now if I have two different deviation vector now, okay, and I want to find, the angle between them, in mathematics, it is actually cos theta, okay, is the cosine of theta, the cosine of an angle actually equal to the what you see here is is the multiplication of two different deviation vector. Of course, you have to transpose the fourth vector or deviation vector before you multiply by the other and divided by the length by the product of the length of the respective deviation vector. Now, I just want to see, I want you to see, okay, if I want to measure relationship between two variables geometrically, okay, if I don't want to go by way of statistics, if I want to do that geometrically, I'm actually going to focus my attention on this. But you know what? When the angle is zero, okay, when this guy is zero, okay, of course, cos zero, we all know the cosine of zero is one, okay. If the, we all know the cosine of zero is actually equal to one. And do you know when you have one? Okay, when you have one, then it actually means the two variables are perfectly correlated. Okay, the two variables are actually they perfectly correlated. You know what that means? You know the way they say it in geometry, they're going to say they have the same orientation. Having the same orientation is more or less like, oh, these two variables is just one. They are the same, in entirety. So when cos zero equal to one, that's what it means. Now, using geometric again, what if it is 180? Cos 180 is negative one. Okay? And when you have negative one, it means they have the same orientation, but in opposite direction. So which mean, two variables are perfectly negatively related. That is what it means. And when theta equal to 90 degree, okay, we all know cos 90, cosine of 90 is zero. Cosine of 90 equal to zero. It actually means the two vectors are perpendicular. Another way we can say that we can say they're going to be orthogonal. Orthogonality means the two vectors are not related at all. They are not related at all. So if I want to look at this statistically now, moving away from the geometric interpretation, I'm actually going to say this guy here, it is the same as this. Okay, of course, you all come across this in basic statistics where you're going to say correlation is the ratio of covariance divided by the product of the respective standard deviation. Okay, I just wanted to take notes of all of this. So, that's that. Now I'm actually moving. Okay, so I think I walked you through this example the other time. Now, do you not know what I want to do now? I want us to look into the real data set. Okay, I want us to look into this three-dimensional example. It is three-dimensional because we got three variables, and of course here the number of observation is three as well. Okay. Now, this may be height, this may be weight. Okay. This may be blood pressure. I'm just assuming. Okay. Of course, blood pressure can be 700 and something. Okay. But let's just say, this represent one variable. This another variable. This is another variable. So if I want to split this out from the matrix form, I want to vectorize each column, then I'm going to have this guy. This guy is this guy, this guy is this guy, this guy is that guy. Okay. Now, if I have them extracted like that, it will be very easy for me to figure out the mean of each column. So I'm going to get the mean of this one, add this one together, divide by 3. You're going to have that. You're going to do the same thing here. You also do the same thing here. So right now, you have the mean for each observation. Okay. Now, when you have the mean for each observation, okay, let me also tell you this. You are dividing by 3 because you are assuming equal weights. The weight here is 1. You are assuming weight of 1, and weight of 1. That's why you are dividing by 3. Or if you are not assuming weight of 1, if they are not equally weighted, it's not going to be divided by 3. Okay, so that's what I mean here. Okay, now after getting this average now, the next thing is, oh, I want to get the deviation. Okay, I also want to get the deviation. I'm going to walk you through. Now, this is actually, showing you how to get the mean, in a you want to look at it from geometrical perspective. Okay, so what I was trying to say, the other time, we got the mean, right? 620. Okay, we are zooming, we are multiplying. If this guy is that mean, oh, 1 second. If this guy, okay, if this guy is the mean that we got, okay, if I want to go this geometric, there's a one here. This particular one here is talking about this guy. Okay, so I'm still going to have, so which means each what this guy is trying to say, okay, in that particular variable, each and every observation in that particular variable has the same average. I'm going to say that again. Each particular observation within that variable has the same average because we are assuming equal weight, okay, to all of them. And that's why you're having 620, 620, 620. Okay, so when you have the 620, 620, 620 now, it will be very easy for you now to find the deviation vector, the deviation vector for that particular variable. So all what you're just going to do is, okay, the data itself, okay, that data, the first variable, the data in the first variable, I'm actually going to go back so that you can see. Okay, so I'm talking about this guy. Or what I'm just going to be doing now, I will be subtracting 620. If I want to get the deviation vector, I'm going to be subtracting 620 from each and every of these data point. If I want to get the deviation vector for this, I'm actually going to be subtracting 650 from each of that. If I want to get the deviation vector here, I'm actually going to be subtracting 680 from each of that. Now, when you do that, I'm going to show you what you actually going to get. Now, D1, okay, which is the first deviation vector, okay, corresponding to the first variable is actually this, okay? Just wanted to take note, okay? Now, there is one thing I want you to see, which also have another statistical meaning. Okay, now that is this we're trying to say, the deviation vector, because we want to look at the relationship, because in order for us to validate our method in statistics, we have assumptions. Okay, I'm going to say this again. You know, well, whenever we specify model and we actually want to provide a practical question a practical answer to problems, okay, we normally have assumptions, okay. Assumptions is what we need to verify before we can validate our model, okay. The assumption here is that the deviation vector has to be perpendicular to the mean. What does that mean? Statistically, there shouldn't be a relationship between a deviation vector and the sample mean. That's what we mean. I'm going to say that again. Don't forget the deviation vector that we're talking about is like a residual in statistics. Okay, it's like a residual. The residual is assumed to be unobserved. Okay, and don't forget this guy is observed. Okay, the mean is observed, and the assumption is that there shouldn't be any relationship between unobserved and observed. Okay, and the geometric interpretation of that is that the deviation vector should be perpendicular. Okay, and if I want to investigate that, what I'm going to do is this. Okay, I'm going to do the transpose. I'm actually going to get the product of the transpose of the deviation vector and the mean. And if I want to prove that perpendicularity or orthogonality, it should give me zero. Okay, that's how we can show. Okay, it should give me zero. And you can see now, okay, this is zero. Okay, so this guy here is what we use now to investigate the orthogonality of the deviation vector and the sample mean. Is there any question before I move to the next slide? Is there any question? If you are good, if you understand this, I need you to say yes or you comment yes.
Yes, sir.
So, okay, thank you so much. Thank you for chatting with me. Okay, I want to move to the next page now. Now, on the next page right now, I think I told you the other time that with the deviation vectors, we are able to perform a successful decomposition of our original observations into sample mean and the deviation vector. And of course, what I have right now actually validates, statistical technique that we all know, which we call the analysis of variance. Okay? And let me tell you this, okay? If there's no variation in the data, if there's no variation at all in the data, if all data actually look the same, I'm expecting deviation to be zero. And the moment I plug in zero here, okay, the moment this guy is zero, then this guy is going to be equal to that guy. Okay, that's exactly what I mean. That is if di equal to zero, and the only condition under which di is going to be equal to zero is when all the data, all the observation within a particular variable stay the same. Okay, that's exactly what I mean. Okay, so let's now see the deviation that we compute. Of course, for the first variable, we have this as deviation. On the second one, we have this as deviation. The third one, we have this as deviation. And let me also tell you this in statistics, if I compute deviation, if I want to know if I'm right, if I add all values in the deviation, it should be zero. Take a look at that. 80, 40, 120 is going to cancel out negative 120. That would be zero. So sum of the deviation has to be equal to zero statistically. Okay, I'm actually moving. And of course, this is we can actually can grab what we got, the deviation in a dimensional space, as you can see right now. And of course, when you have them, you can see the way you can see angle. Okay, if you want to know what is the angle between that and that, so angle exists. Okay, now I want to walk you through how to get the variances. We've gotten the mean of each variable. We've gotten the deviation vector for each variable. Okay, we now want to get the variances because why do we need the variances? Of course, we may actually be interested in how the data spread out. Okay, so let me tell you this. Do you know that one thing lead to the other? Okay, so the length of the deviation now, okay, if I'm talking about the first variable, Okay, the length of the deviation, mathematically, the length of the deviation is actually this. Okay, so the deviate, the other time, don't forget, you know, the deviation that I got for D1. I'm actually going to show you now. Okay, so the deviation for that. Okay, we got 80, -120, and 40. So we actually want to work on that now. Okay, so if I get the length of that, I'm actually going to square that and that will give me this result. Now, geometrically, this is the length of deviation for the D1, and statistically speaking, okay, we can actually equate that to this guy. Okay, we are X11. When I say X11, okay, X11 is actually talking about the variance of a particular variable. So what I'm trying to say in essence is that there's a relationship between the length of deviation, that is, I mean, the deviation, the deviator vector length actually equal to this, and x11 is a variance we're looking for. So I'm just going to solve this equation. Of course, I know my n equal to 3. Okay, I'm only going to solve this, then I'll be able to get my x1. This is my x11 now. Okay, my x11. So my variance right now, okay, from this process, my variance is actually this. This is my variance. Okay. I also, if I want to get my standard deviation, I'm going to find the square root of variance. You see that now? I got my variance, I got my standard deviation. Okay. Now I'm going to also do that to the second variable. Okay. I'll do that to the second variable. Then I'm also going to do that to the top variable, as you can see right now. Okay. Can you see that? Now, I can also proceed to the correlation as well. Now, for the correlation, you can see if I want to obtain my correlation using the formula I showed you the other time, don't forget the cosine equal to this. So when I got that, I'm actually getting my correlation. So you can see what I'm doing here. Or just a combination. This is just a product of the transpose of the first deviation vector multiplied by the deviation vector for the second variable is what you have here. We've gotten D1, D2 the other time. Then we're also going to get the length. Okay, you remember when we got in the length, we're going to say the square root. Okay, can you see all of that? The square root of something square, square like that. And at the end of the day, I'll be able to get my correlation. Okay, so here, and if I want to get the angle, let's say for instance, if I have a correlation given like this, what is the angle? Of course, uh, don't forget, right here, what is equal to this guy is the cosine. Is the cosine of theta? Okay, is a cosine of theta. So if I want to get if the cosine of theta is equal to this, if I want to get theta, I'm actually just going to find the inverse of the cosine that we actually call arc cos. Now the angle here is 40.89 degree. If I really want to know the angle, okay, so I'm actually going to do that to you know, all the possible pairwise combination. Okay, just wanted to see that. Okay, now I'm actually moving. Now, this is the summary, and I've explained all this the other time. Okay, the axes of the observation space are defined by cases, which is or individuals, and the variables are represented as vectors. And I talk about the projection, okay? The projection of y of the data, okay, onto the equal angular vector 1 actually give rise to the mean, right? Okay, so what about if we are looking for the information contained in the sample covariance matrix, we can actually obtain that from the deviation vector. Okay, so which means four of us need to get the deviation of vector, and after getting the deviation vector, I will be able to get my variance or using this relationship. Take a look at this guy or using this relationship. Okay, I'll be able to get a particular variance, the SKK. Okay, SKK. is the variance of a particular variable. If I want to get the variance of the first variable, it's going to be S11. If I want to get the variance of the second variable, that's going to be S22. If I want to get the variance of the third variable, that would be S33. And if I want to get a covariance, okay, maybe I want to get the covariance S12 or S13 and so on. Of course, this is actually what I'm going to use. And of course, if I want to figure out the angle between two deviation vector, of course, what I'm actually going to use is going to be a cosine theta or equal to what I showed you before. Okay, now uh, I think this is where I'm actually going to start from on Friday. So on Friday, I'm going to start from random sample and expected values. Before I go today, is there any question? Of course, on Friday we're returning to in person. We're gonna be in class on this Friday. So, is there any question before I go today? Is there any question? Okay. In the absence of question, make sure you all stay safe. Okay. I'm gonna see you in class on Friday. Bye for now, everyone. See you on Friday.
Thank you.
You welcome.